In 1900, physicist Lord Kelvin famously declared that physics was essentially complete, with only a few minor details left to work out. Within 5 years, Einstein published his theory of special relativity, shattering classical physics. Within 25 years, quantum mechanics had demolished our understanding of reality at the smallest scales. Kelvin's confidence was spectacularly misplaced. Today, we stand at another potential turning point, but this time the question is more radical than anything Einstein or the quantum pioneers imagined. What if the universe has no fundamental speed limit? What if there's no maximum temperature? What if energy itself can be infinite? These aren't idle speculations, they're serious questions emerging from the bleeding edge of physics, where our most sacred assumptions about physical limits are being challenged by theories and observations that suggest reality might be far stranger than we ever dared imagine. What you're about to discover will make you question everything you think you know about the possible and the impossible. For over a century, one fact has seemed absolutely fundamental to physics: nothing can travel faster than light. Einstein's special relativity, published in 1905, established the speed of light, 299,792,458 meters per second, as the universe's ultimate speed limit. This isn't just a speed limit like highway rules that you could theoretically break, it's woven into the fabric of space-time itself. As objects approach light speed, bizarre things happen. Mass increases. A spaceship approaching light speed would gain mass, requiring exponentially more energy to accelerate further. Time dilates. Clocks on the ship would run slower relative to stationary observers. Length contracts. The ship would physically shrink in the direction of motion. Energy requirements approach infinity. Reaching exactly light speed would require infinite energy. These aren't hypothetical predictions, they're confirmed by countless experiments. Particle accelerators routinely accelerate subatomic particles to 99.9999% the speed of light, and the particles behave exactly as relativity predicts. The theory has been tested to extraordinary precision and has never failed. The cosmic speed limit isn't arbitrary. It emerges from the fundamental structure of space-time. Space and time are not separate things but unified into space-time, and the speed of light is the conversion factor between space and time, the speed at which all things move through space-time, whether they're moving through space or sitting still, in which case they're moving through time at maximum rate. Einstein's equations show that massive objects simply cannot reach light speed. Massless particles like photons travel at exactly light speed and cannot go slower. Anything with mass must travel slower than light. This limit has profound implications. No faster than light communication. Information cannot travel faster than light, preventing causality violations. The observable universe is finite. Light from distant galaxies hasn't had time to reach us, creating a cosmic horizon. Time travel paradoxes are avoided. You can't go back in time by exceeding light speed. For generations, physicists accepted this as fundamental reality. The speed of light isn't just a limit, it's the limit, woven into the mathematical fabric of the universe. But what if we've been wrong? In 1967, physicist Gerald Feinberg proposed something radical. What if particles exist that always travel faster than light? He called them tachyons, from the Greek word for swift. Tachyons aren't ordinary particles that somehow accelerate past light speed. That remains impossible. Instead, tachyons would be particles that have always been travelling faster than light, just as ordinary particles have always been slower than light. They'd inhabit a completely different realm of physics. The mathematics of tachyons is bizarre. Imaginary mass. Tachyons would have to have imaginary mass, literally the square root of a negative number. This sounds nonsensical, but in physics, imaginary is a technical term. It means their mass-energy relationship follows different rules than normal matter. Reversed energy-speed relationship. For tachyons, losing energy would make them speed up, while gaining energy would slow them down. A tachyon with infinite energy would travel at exactly light speed, but from the fast side, while a tachyon with zero energy would travel infinitely fast. Time travel implications. Tachyons could theoretically transmit information backward in time, creating causality paradoxes. If you could send a tachyon message to your past self, you could create paradoxes like telling yourself not to send the message. creating an impossible loop. Observable signatures. If tachyons exist, they might produce detectable effects, perhaps Cherenkov radiation, the light equivalent of a sonic boom, as they move through spacetime faster than light moves through spacetime. The problem? Despite decades of searching, no one has found evidence of tachyons. Particle accelerators, cosmic ray detectors, and astronomical observations have all come up empty. If tachyons exist, they're extraordinarily rare or don't interact with normal matter in detectable ways. Most physicists consider tachyons mathematical curiosities rather than real particles. The equations of relativity technically allow them, but nature doesn't seem to have implemented them. Yet the tachyon hypothesis opened an important door. It showed that the speed of light being a limit is not logically necessary. The universe could have been different, and some physicists wonder if perhaps, in some domains, it is different. Quantum mechanics revealed something that seems to violate Einstein's speed limit: entanglement. When two particles are quantum entangled, measuring one particle instantaneously affects the other, regardless of the distance between them. Einstein called this spooky action at a distance and believed it proved quantum mechanics was incomplete. Here's the bizarre reality. Entangle two particles, say photons with correlated polarizations, separate them by any distance, across a lab, across the planet, across the galaxy. Measure one particle's property, like its polarization, the other particle's property is instantaneously determined. The correlation is perfect and instantaneous. When you measure the first particle's polarization, the second particle's polarization is immediately fixed to be correlated with it, even if the particles are light years apart. This seems to violate relativity's prohibition on faster-than-light information transfer. If I measure a particle here on Earth, and it instantly affects an entangled particle on Mars, hasn't information traveled faster than light? The subtle answer is no, but the reasoning is complex. No usable information is transmitted. When you measure the first particle, you get a random result. You can't control what result you get, so you can't encode a message. The correlation between the particles is only visible when you compare measurements after the fact, and that comparison requires classical communication at light speed or slower. The correlation exists timelessly. Quantum mechanics treats the entangled pair as a single quantum system until measurement. The correlation doesn't travel from one particle to the other. It was always there in the quantum state describing both particles. No causality violation. Because you can't use entanglement to send information faster than light, you can't create causality paradoxes or violate relativity's deeper principles. So entanglement doesn't actually violate the cosmic speed limit, but it shows that reality has aspects that are non-local. The universe contains connections that transcend space and time in ways that classical physics never imagined. And this opens a fascinating question. If reality can be non-local in this limited way, might there be other ways in which the speed limit is not quite as absolute as we thought? In 1994, physicist Miguel Alcubierre proposed something that sounds like science fiction, but is based on rigorous application of Einstein's general relativity. A faster-than-light drive that doesn't actually violate relativity. The trick is deceptively simple. Don't move through space faster than light. Move space itself. General relativity shows that spacetime is flexible. Massive objects curve spacetime, creating gravity. But the equations also allow spacetime to expand or contract. During cosmic inflation, space expanded faster than light. The distant galaxies are receding from us at superluminal speeds, not because they're moving through space, but because space between us and them is expanding. Alcubierre asked, could we create a controlled warp bubble that contracts space in front of a spacecraft and expands it behind? The ship would surf a wave of spacetime, covering vast distances while locally never exceeding light speed. Inside the warp bubble, spacetime would be flat and normal. The ship wouldn't experience acceleration, time dilation, or any relativistic effects. Passengers could drink coffee and read newspapers while moving at effective speeds millions of times faster than light. The mathematics works. Alcubierre's metric, the mathematical description of curved spacetime, is a valid solution to Einstein's field equations. In principle, if you could manipulate spacetime as required, you could travel from Earth to Alpha Centauri in days instead of years, all without violating relativity because you never locally exceed light speed. The problems? Exotic matter required. Creating an Alcubierre drive requires matter with negative mass-energy density, something that repels rather than attracts. We've never observed macroscopic negative energy, though quantum mechanics allows tiny amounts in specific circumstances through phenomena like the Casimir effect. Enormous energy requirements. Early calculations suggested you'd need more energy than exists in the observable universe. Later refinements reduced this to merely the mass energy of Jupiter, still absurdly beyond our capabilities. Causality concerns. Some physicists argue that Alcubierre drives would allow time travel to the past, creating paradoxes. If you can outrun light, you can potentially close time-like curves, paths through spacetime that loop back to their starting point in time. Stability issues. The warp bubble might be unstable, collapsing before it could be useful. Quantum effects might destabilize it. We don't know because we can't build one to test. Still, the Alcubierre drive demonstrates something profound. The speed of light is a local limit, not necessarily a universal one. You can't go faster than light through space, but space itself has no speed limit. This distinction might be exploitable. Recent research by Dr. Eric Lentz at the University of Göttingen proposed modifications to the Alcubierre drive that might eliminate the need for negative energy, using only positive energy densities configured in specific ways. His soliton solutions show warp bubbles that travel faster than light using theoretically possible energy configurations. The energy requirements are still astronomical, equivalent to hundreds of times Jupiter's mass. But that's an engineering challenge, not a fundamental physical impossibility. The distinction matters. Every physics student learns about fundamental constants: the speed of light, Planck's constant, the gravitational constant. These aren't arbitrary. They're woven into nature's fabric. Combining these constants in specific ways gives you the Planck units, fundamental scales where our current physics theories break down. Planck length, 1.6 times 10 to the negative 35th meters, the scale where quantum effects dominate spacetime itself. Planck time, 5.4 times 10 to the negative 35th seconds, 10 to the negative 44 seconds, the smallest meaningful time interval. Planck energy, 1.22 times 10 to the power of 19 giga-electron volts, the energy scale where quantum gravity becomes important. The Planck energy is extraordinary, roughly 2 billion joules concentrated in a single particle, equivalent to the kinetic energy of a car traveling at highway speed, but in something smaller than an atom. Why does this matter for limits? Because at Planck energy, our theories predict that physics as we know it breaks down completely. Spacetime becomes foamy. At Planck scales, quantum fluctuations make spacetime itself turbulent and chaotic. The smooth fabric of space and time dissolves into a froth of quantum uncertainty. General relativity and quantum mechanics clash. Our two most successful theories, general relativity, describing gravity and spacetime, and quantum mechanics, describing the very small, give contradictory predictions at Planck scales. Both can't be right, meaning our understanding is incomplete. Black holes become elementary particles. At Planck energy, a particle's quantum wavelength equals its Schwarzschild radius, the size a black hole with that mass would be. The distinction between a particle and the black hole becomes meaningless. New physics must emerge. Something beyond our current theories must govern physics at Planck scales. String theory, loop quantum gravity, and other proposals attempt to describe this regime, but we have no experimental access to these energies. Here's the provocative part. We assume Planck energy is a limit because our theories break down there. But what if the breakdown of our theories doesn't mean nature has a limit? It means our understanding is limited. Imagine trying to understand the ocean using only the physics of ice. Ice has a maximum temperature before it melts. Does that mean temperature is fundamentally limited? No, it means ice physics breaks down, and you need to understand water. Perhaps Planck energy isn't a fundamental limit, but a phase transition where physics becomes something we don't yet understand. Maybe beyond Planck scales, new phenomena emerge that have no limits we currently comprehend. Temperature seems to have an absolute lower limit, absolute zero or minus 273.15 degrees Celsius. At absolute zero, atoms stop moving, except for quantum jitters. You can't go colder because there's no more energy to remove. But what about the upper limit? is there a maximum temperature? Conventional physics says yes, the Planck temperature, about 1.4 times 10 to the power of 32 Kelvin. This is so hot that physics as we know it breaks down. It's the temperature the universe had in the first 10 to the minus 43 seconds after the Big Bang. Beyond Planck temperature, quantum gravitational effects dominate. Space-time itself would boil with energy. Our equations give nonsensical answers. It seems like a fundamental limit. But then there's the bizarre phenomenon of negative absolute temperature. In specialized quantum systems, physicists have created states with negative Kelvin temperatures. This sounds nonsensical. How can temperature be below absolute zero? But it's technically different. Negative temperature states are actually hotter than infinite temperature. Here's how it works. Temperature is defined by energy distribution. In normal systems, adding energy increases the average particle energy, which we perceive as higher temperature. There are always higher energy states available for particles to occupy. Some quantum systems are different. In systems with a maximum possible energy state, like certain magnetic spin systems, you can create an inverted population where more particles are in high energy states than low energy ones. Inverted populations have negative temperature. Mathematically, this situation corresponds to negative Kelvin. Counterintuitively, negative temperature is hotter than positive temperature. Energy flows from negative to positive temperature systems. The temperature scale actually wraps around 0 Kelvin to positive temperatures, to plus infinity Kelvin to minus infinity Kelvin, to negative temperatures to 0 Kelvin. In 2013, physicists at the Ludwig Maximilian University of Munich created a gas of potassium atoms at negative temperature. The atoms wanted to give off energy to anything colder, and everything is colder than negative temperature, even things at billions of degrees. This demonstrates that our intuitive understanding of temperature limits is incomplete. The scale has topology, it loops back on itself. What we thought was an absolute maximum, infinite temperature, is actually a transition point to another regime. Does this mean temperature truly has no limit? Not exactly, but it shows that limits can be more subtle than we imagine. Physics often has apparent limits that turn out to be transitions to new regimes rather than absolute boundaries. Quantum mechanics makes a stunning prediction. Empty space isn't empty. Even in a perfect vacuum with no particles, quantum fields undergo constant fluctuations. Virtual particles pop in and out of existence. These fluctuations carry energy, vacuum energy. Calculating how much vacuum energy should exist is straightforward using quantum field theory. The answer is shocking. Quantum field theory predicts the vacuum should have an energy density of about 10 to the power of 113 joules per cubic meter. Observations show the actual vacuum energy, measured as dark energy causing cosmic acceleration, is about 10 to the negative 9th joules per cubic meter. The prediction exceeds observation by 120 orders of magnitude, the worst prediction in the history of physics. This is called the cosmological constant problem, or the vacuum catastrophe. If quantum mechanics is correct, the vacuum should contain almost infinite energy. Space itself should be impossibly dense with energy. Why don't we see this? Several possibilities exist. Cancellation mechanism. Maybe various quantum contributions to vacuum energy almost perfectly cancel, leaving a tiny residual. But this would require fine-tuning to 120 decimal places, so precise it seems absurd. Our theory is wrong. Maybe our quantum field theory calculations are fundamentally mistaken. But quantum field theory successfully predicts other phenomena to extraordinary precision. How can it be so right, yet so wrong about vacuum energy? Vacuum energy is truly infinite, but perhaps the vacuum does contain infinite energy, but it doesn't gravitate the way we expect. Einstein's equations might need modification to account for why vacuum energy doesn't curve spacetime as much as it theoretically should. Anthropic principle. In a multiverse with different vacuum energies in different regions, only regions with low vacuum energy would develop structures, stars, and life to observe it. We see low vacuum energy because we couldn't exist otherwise. This explanation is philosophically troubling. It explains by removing the need for explanation. Something beyond current physics. Maybe at very high energies or very small scales, physics operates under rules we haven't discovered. Vacuum energy might be self-limiting through mechanisms we don't yet understand. The vacuum energy problem suggests that reality might contain infinite or near-infinite energy, but our equations fail to properly account for how that energy manifests. It's a hint that power itself, in the form of energy density, might not have the limits we assume. General relativity predicts singularities, points where quantities like density, curvature, and gravitational field strength become infinite. Black hole singularities. At the center of every black hole, general relativity predicts all matter is crushed to infinite density in a single point. Curvature becomes infinite. The gravitational field is infinite. Big Bang singularity. Tracing the universe backward in time, general relativity predicts that 13.8 billion years ago, everything was compressed into a single point of infinite density and temperature. Physicists universally agree these infinities aren't real. They signal where our theories break down. But they raise a provocative question. What if the infinities are pointing toward real aspects of nature that transcend our mathematical descriptions? When Einstein's equations give infinite answers, we say the equations have reached their limit of applicability. Quantum gravity, whatever form it takes, should resolve these singularities, replacing infinities with large but finite values. Or should it? Some radical theorists ask, what if the resolution isn't removing the infinities, but understanding them differently? What if singularities represent transitions to regimes where power genuinely has no limit, but in ways that don't affect the external universe the way we'd naively expect? Roger Penrose proposed that singularities might be cosmic censorship. They're always hidden behind event horizons, preventing the infinities from affecting the outside universe. Black hole singularities are inside event horizons. The Big Bang singularity is in the past, behind the cosmic horizon. We never actually encounter naked infinities. But what does this mean? Are the infinities real but quarantined? Or are they artifacts of missing physics? The answer might reshape our understanding of limits. String theory, the leading candidate for a theory of everything, unifying quantum mechanics and gravity, makes a startling claim. Reality has more dimensions than we perceive. The most developed version, M-theory, proposes that spacetime has 11 dimensions, the 3 spatial dimensions and 1 time dimension we experience, plus 7 additional spatial dimensions curled up so small we can't detect them. Why can't we see these extra dimensions? They're compactified, rolled up into spaces smaller than the Planck length, invisible at accessible energy scales. But here's where it gets wild. The mathematics of string theory suggests that the specific way dimensions compactify determines the physics we observe. Different compactifications give different particle masses, different force strengths, different physical laws. And here's the kicker. There might be 10 to the power of 500 or more possible compactifications. A number so large, it's called the landscape of string theory. Each compactification is potentially a different universe with different physics, different speed limits, different maximum temperatures, different fundamental constants, different particles and forces. In this framework, the limits we observe aren't fundamental, they're environmental, determined by how extra dimensions happen to be configured in our particular universe. Moreover, some compactifications might have qualitatively different properties. Varying speed limits. In some configurations, the effective speed of light might be different. Perhaps some even have no speed limit at all, with different casualty structures than we experience. Infinite dimensional spaces. Some string theory solutions involve infinite dimensional spaces, not just extra dimensions, but genuinely infinite dimensional manifolds. What would physics look like in such spaces? Dynamical limits. Perhaps the limits we observe aren't fixed, but evolve over cosmic time as the extra dimensions slowly change configuration. Early universe physics might have had different limits than today. String theory is speculative. We have no experimental confirmation, but it demonstrates that within mathematically rigorous frameworks, the limits we observe need not be universal or absolute. They could be contingent properties of our particular cosmic environment. Philosopher Nick Bostrom's simulation argument proposes that we might be living in a computer simulation created by an advanced civilization. While often dismissed as science fiction, The hypothesis raises serious questions about limits. If reality is a simulation, then the physical limits we observe might not be fundamental constraints of reality itself. They might be computational or design choices by the simulators. Consider the speed of light as frame rate. In computer games, there's a maximum speed at which information propagates, determined by the game's update rate. If reality is simulated, the speed of light might be analogous, a maximum rate at which the simulation updates causal connections. Planck scale as resolution limit. Video games have maximum resolution, individual pixels below which no detail exists. Perhaps Planck length is the pixel size of reality, not a fundamental physical scale but a computational resolution limit. Quantum randomness as computational efficiency. Quantum mechanics doesn't determine precise particle positions until measured. Maybe this isn't fundamental uncertainty but a computational trick. The simulation only renders details when observed, saving processing power. Conservation laws as memory management. Maybe energy conservation isn't a deep physical principle but a computational constraint. The simulation must keep track of a finite amount of energy currency to manage memory. If this is even remotely correct, it suggests two possibilities. Limits are real but not fundamental. The limits we observe are artifacts of the simulation's design and computational constraints, not properties of ultimate reality. The simulation runs on hardware in a base reality that might have completely different or no limits. Limits are hackable. If reality is software, then sufficiently advanced beings might find ways to exploit glitches or modify parameters. What we think are unbreakable physical laws might be more like software constraints that can be circumvented with enough understanding. The simulation hypothesis is unprovable with current methods. Any evidence could be part of the simulation, but it illustrates that even within serious philosophical frameworks, the idea that observed limits might not be fundamental is taken seriously. Mathematics routinely deals with infinity. We have infinite sets, natural numbers, real numbers, infinite sequences, infinite series. Mathematicians work with different sizes of infinity, countable versus uncountable, and have rigorous frameworks for reasoning about infinite quantities. But does mathematical infinity correspond to anything physical? Most physicists say no. Physicist Max Tegmark distinguishes between mathematical and physical infinity. Mathematical infinity is an abstract concept, a tool for reasoning about processes that continue without bound, or sets that have no largest element. Physical infinity would mean actual infinite quantities existing in nature, infinite energy, infinite density, infinite temperature. The consensus is that physics might use mathematical infinity as a tool, but doesn't contain physical infinities. When our theories predict infinities, like at black hole singularities, we interpret that as theory breakdown, not actual infinities. But is this consensus justified? Cosmology provides interesting challenges. Is space infinite? We don't know. The universe might be spatially infinite, extending forever in all directions, or finite but unbounded, wrapping back on itself. Current observations are consistent with flat, infinite space, but we can't be sure. Are there infinitely many particles? If space is infinite and matter is distributed uniformly, as observations suggest on large scales, then there are infinitely many atoms, stars, and galaxies. This would be a real physical infinity. Does time extend infinitely? Into the past? Probably not. The Big Bang was a beginning. Into the future? Maybe. Some cosmological models suggest eternal expansion. Time might be unbounded into the future, representing another physical infinity. Some physicists argue that physical infinities are not just possible, but necessary. Infinity is simpler than large, finite numbers. Physicist Sean Carroll points out that a theory with infinite space is actually simpler, Occam's razor, than a theory requiring an arbitrary large but finite size. Why would space end at exactly 10 to the 30 meters? Infinity removes the arbitrary cutoff. Renormalization suggests hidden infinities. Quantum field theory routinely deals with infinities through renormalization, a mathematical process that absorbs infinities into redefined parameters. Maybe these aren't just mathematical tricks, but hints that nature fundamentally involves infinities managed in clever ways. Limits might be emergent, not fundamental. Just as temperature emerges from underlying atomic motion, maybe limits like light speed emerge from deeper physics where no such limits exist. The question remains unresolved. Are the limits we observe fundamental properties of reality, or are they emergent features of physics at accessible scales, with unlimited quantities lurking at deeper levels? Quantum mechanics reveals something strange about limits. Before measurement, quantum systems exist in superpositions, combinations of multiple states simultaneously. The possibilities are, in a sense, unlimited until observation forces a particular outcome. Consider the famous double-slit experiment. Shoot electrons at a barrier with two slits. Each electron passes through, both slits simultaneously. Creates an interference pattern only possible if each electron went through both slits. But if you measure which slit the electron went through, the pattern disappears. Each electron goes through one slit or the other. Before measurement, the electron is in a superposition of all possible paths. It's not that we don't know which path it genuinely took all paths simultaneously. This extends to other properties, position and momentum. Until measured, a particle doesn't have a definite position or momentum. It exists as a probability wave spread across space. Energy and time. The Heisenberg uncertainty principle allows energy to fluctuate by arbitrarily large amounts, as long as the fluctuation is brief enough that delta E times delta T is approximately h bar. Spin and polarization. Unmeasured particles exist in superpositions of all possible spin states simultaneously. In the many worlds interpretation of quantum mechanics, this goes even further. Every quantum possibility actualizes in some branch of reality. When you measure an electron's spin, the universe splits into branches where you observed spin up and branches where you observed spin down. Both outcomes are equally real, existing in parallel universes. If many worlds is correct, then reality has no limits on possibilities. Every quantum outcome occurs somewhere. The infinity of quantum possibilities becomes an infinity of actual universes, each exploring different outcomes. Even in more conservative interpretations, quantum mechanics shows that before measurement, systems aren't limited to single definite values. They embody unlimited potentiality that collapses to specificity only upon observation. This raises a profound question. Are the limits we observe, definite particle positions, momenta, energies, properties of reality itself, or properties of what happens when we measure reality? Is the limitation in nature, or in our interaction with nature? One of the most revolutionary ideas in modern physics is the holographic principle, emerging from black hole thermodynamics and string theory. The principle states, the information content of any region of space is proportional not to its volume, but to the area of its boundary. A spherical region can contain at most about 10 to the 69th power bits of information per square meter of its surface area. This seems to impose a fundamental limit on information density, and by extension, on energy and complexity. But the holographic principle also suggests something radical. Three-dimensional space might be an illusion. The fundamental reality might be a two-dimensional surface, like the universe's boundary, where information is encoded, with three-dimensional space emerging as a holographic projection from that surface. If true, this inverts our understanding of limits. 3D limits might not be fundamental. The limits we observe in 3 dimensions, speed of light, Planck energy, maximum information density, might be projections from a different regime where different or no limits apply. Dimensionality itself might be dynamic. If dimensions are emergent from more fundamental information structures, then the number of dimensions and their properties, including the limits they impose, might be contingent rather than absolute. Information might be the true unlimited quantity. If information is more fundamental than energy or space, and if information can be distributed across boundaries in complex ways, perhaps information itself has no fundamental limit, even though its projections into spacetime appear limited. The holographic principle is still being developed, with connections to quantum gravity and string theory, but it exemplifies how modern physics is discovering that what we thought were fundamental limits might be emergent features of particular descriptions, rather than absolute constraints. The multiverse hypothesis proposes that our universe is one among perhaps infinitely many universes, each potentially having different physical laws, constants, and limits. Several independent lines of reasoning suggest multiverses. Eternal inflation. Cosmic inflation, which drove the universe's early expansion, might be eternal, constantly creating new bubble universes with different properties. Each bubble would be a separate universe with potentially different physics. String theory landscape. As mentioned earlier, the vast number of possible string theory compactifications might correspond to different universes, each exploring a different configuration. Many worlds quantum mechanics. Every quantum measurement spawns new branches of reality, creating an ever-expanding tree of universes, exploring all quantum possibilities. Mathematical multiverse. Physicist Max Tegmark proposes that every consistent mathematical structure exists physically as a universe. If true, there would be infinite universes with all possible mathematical physics. In a multiverse, the limits we observe aren't universal, they're local to our particular universe. Other universes might have different speed limits, faster or slower than light or none at all, different maximum temperatures, different numbers of dimensions, different particles and forces, different or no quantum mechanics, different or no relativity. Some universes might be simpler than ours, with fewer types of particles and forces. Others might be vastly more complex, with additional forces and phenomena we can't imagine. If the multiverse is real, then fundamentally power has no limit, because across the multiverse, all possible powers, energies, and configurations exist somewhere. Our observed limits are parochial, specific to our particular cosmic neighborhood. Of course, multiverse theories are controversial. They're difficult or impossible to test. We can't visit other universes to see if they exist. Some physicists argue multiverse theories aren't really science because they don't make testable predictions. Others counter that multiverse theories emerge naturally from our best theories, inflation, string theory, quantum mechanics, and explain otherwise puzzling fine-tuning in our universe's physics. Whether they're true or not, they demonstrate that serious physics can consistently describe scenarios where limits are local rather than universal. Here's the most speculative and philosophical question. Might consciousness transcend physical limits? This isn't mysticism. It's a genuine puzzle in philosophy of mind and physics. Consciousness seems different from other physical phenomena. Subjectivity. Consciousness involves subjective experience, what it's like to see red, feel pain, or think a thought. Physics describes objective, third-person phenomena. How does subjective experience arise from objective physical processes? Unity. Consciousness seems unified. You have a single stream of experience, not billions of separate experiences corresponding to your billions of neurons. How does unity emerge from distributed physical processes? Intentionality. Consciousness is about things. Thoughts are always about something. How does aboutness arise from physical interactions? These puzzles have led some philosophers and physicists to consider panpsychism, the idea that consciousness is a fundamental feature of reality, present, in some form, at all scales, not just in brains. Physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that consciousness involves quantum processes in brain microtubules, potentially connecting to the fundamental quantum structure of spacetime itself. If consciousness is fundamental rather than emergent, it might not be subject to the same limits as physical processes. Could consciousness access information faster than light? Some interpretations of quantum mechanics suggest observer consciousness plays a role in wave function collapse. If so, consciousness might interact with quantum reality in ways not limited by spacetime. Could consciousness survive physical death? If consciousness is fundamental, and not purely generated by brain activity, then perhaps it persists beyond the brain's dissolution, not as superstition but as a physical possibility in theories where consciousness is built into reality's foundation. Could consciousness expand without limit? Perhaps individual consciousness is a localized manifestation of a universal consciousness field. Expanded states of awareness might access aspects of reality beyond ordinary limits. These ideas are highly speculative and controversial. Most neuroscientists believe consciousness is entirely generated by brain activity and subject to all normal physical limits. But the hard problem of consciousness, explaining how subjective experience arises from objective physical processes, remains unsolved. Until we understand consciousness's relationship to physics, we can't definitively say whether consciousness transcends physical limits or not. Let's imagine that some or all of the above speculations are correct, that the universe doesn't have absolute limits on speed, energy, or information, or that such limits are local rather than universal. What would this mean?
Technology beyond imagination.
If faster-than-light travel is possible through space-time manipulation or other exotic means, humanity could eventually explore the galaxy and beyond. The vast distances that make interstellar travel seem impractical would become manageable. If vacuum energy can be tapped, we'd have access to essentially unlimited power. Energy scarcity would become obsolete. Climate change, resource depletion, and energy-related geopolitics would be solved. If quantum computing can scale without fundamental limits, we could simulate arbitrarily complex systems, perhaps even consciousness itself. We might create artificial minds indistinguishable from or exceeding human intelligence. If the Planck scale isn't a hard limit but a transition to new physics, technology operating at those scales might manipulate space-time itself, create or destroy matter at will, or access higher dimensions. Existential hope and terror. Unlimited power is both tremendously hopeful and terrifying. On the hopeful side, a civilization that masters unlimited power could solve virtually any physical problem. Disease, aging, death itself might become optional. Biological processes could be precisely controlled at quantum levels. Consciousness might be uploadable, copyable, or extendable indefinitely. Resource limitations would disappear. Humanity could expand indefinitely through the cosmos. But the terror is equally profound. The destructive potential scales with creative potential. If vacuum energy can be harnessed for unlimited power, it could also create weapons of unimaginable destruction. A single individual with access to such technology could potentially destroy planets, stars, or even galaxies. Unlimited power doesn't guarantee wisdom. History shows that humans often wield power irresponsibly. Give humanity unlimited energy while we still have tribal conflicts, ideological extremism, and short-term thinking, and the result could be catastrophic. The control problem intensifies. If we create artificial superintelligence with access to unlimited power, ensuring it remains aligned with human values becomes even more critical. A misaligned superintelligence with unlimited power could reshape reality in ways utterly hostile to human flourishing.
Existential risk from experimentation. If physicists discover ways to manipulate reality at fundamental levels, creating mini black holes, tearing space-time, or triggering vacuum decay, a laboratory accident could potentially destroy everything. The more powerful our tools, the greater the consequences of errors. The Fermi paradox gets darker. If power has no fundamental limits, the Fermi paradox, where is everybody, becomes even more disturbing. Perhaps advanced civilizations inevitably discover unlimited power, and perhaps unlimited power inevitably leads to self-destruction. Maybe there's a great filter ahead of us. Civilizations that survive to technological maturity inevitably gain access to unlimited power, and almost all of them use it to destroy themselves, either accidentally or deliberately. Or perhaps civilizations that discover unlimited power transcend physical existence entirely, becoming undetectable to civilizations still operating within normal physics. They might exist in higher dimensions, different universes, or states of being we can't comprehend. Or, darkest of all, perhaps a civilization that gains unlimited power first establishes dominance over the galaxy or universe, preventing other civilizations from arising or expanding. We don't see anyone else because someone got there first and maintains control. The simulation hypothesis becomes more plausible. If power is unlimited, then creating simulations of arbitrary complexity becomes feasible. An advanced civilization could simulate entire universes with billions of conscious beings, each unaware they're simulated. If one real universe can host millions or billions of simulated universes, then statistically, most conscious beings exist in simulations rather than base reality. You're more likely to be simulated than real. This raises vertiginous questions. How many layers deep are we? Is there a base reality at all? Or is it simulations all the way down? If we're simulated, do the limits we observe reflect fundamental reality, or merely the simulator's choices? And here's the twist. If we're in a simulation,
and power truly has no limits in base reality, then potentially we could
discover the simulation's parameters and hack them, modifying our reality's rules, communicate with the simulators, perhaps persuading them to grant us more power or freedom, escape the simulation by uploading ourselves to the simulator's reality, create our own simulations, becoming gods to simulated beings within our universe. Each of these possibilities transforms from science fiction to theoretical possibility if power is truly unlimited. The nature of reality becomes radically uncertain. If the limits we observe aren't fundamental, then we can't trust our most basic intuitions about reality. Causality might be negotiable. We assume cause precedes effect, but if faster than light or backwards in time signaling is possible, causality becomes flexible. Reality might contain causal loops, retrocausal effects, or acausal connections we can't currently perceive. Time might not be what it seems. We experience time as flowing forward, but physics treats time as just another dimension. If we could access higher dimensional spaces or manipulate space-time directly, we might be able to move through time as freely as we move through space. Matter and energy might be illusions. If the holographic principle is correct, and 3D space is a projection from 2D information, then matter and energy might be convenient descriptions of something more fundamental, perhaps pure information or mathematics itself. Mathematics might be reality. Physicist Max Tegmark's mathematical universe hypothesis proposes that reality is mathematics, literally, not metaphorically. Physical existence is just mathematical existence. If true, then anything mathematically consistent exists somewhere, and power limits are just features of particular mathematical structures, not universal constraints. The philosophical crisis. Perhaps the deepest implication of unlimited power is philosophical rather than practical. For millennia, human thought has been structured around scarcity and limitation. Ethics evolved around limited resources. Most moral questions involve how to fairly distribute limited goods, food, wealth, power, opportunities. If resources become unlimited, traditional ethics might become obsolete. What does fairness mean when everyone can have anything? Meaning emerged from limitation. Much of what gives life meaning involves overcoming constraints, achieving goals despite obstacles, creating beauty within limitations, finding purpose through struggle. If all constraints vanish, do achievements become meaningless? Does creativity require limitation? Identity involves boundaries. We define ourselves partly through our limitations, our mortality, our capabilities, our circumstances. If bodies become optional, minds upgradable, and lifespans unlimited, what happens to personal identity? Are you still you if every aspect of your existence becomes fluid and unbounded? Death gave urgency to life. Knowing we'll die motivates us to prioritize, to make choices, to invest experiences with significance. If death becomes optional or reversible, does life lose its urgency? Do choices matter less when everything can be undone? These aren't abstract questions. If power truly has no limits, we'll face them practically. Societies will need to develop new philosophical frameworks for meaning, ethics, and identity in a post-scarcity, post-mortal, potentially post-physical existence. Some find this prospect exhilarating. Unlimited power as the key to solving all problems and achieving all dreams. Others find it horrifying. Unlimited power as the destruction of everything that makes existence meaningful. Before we get too carried away with speculation about unlimited power, let's examine the strong case for why the limits we observe probably are fundamental. Empirical track record. Every time we've tested the speed of light limit, it's held. Particle accelerators, astronomical observations, GPS satellite corrections, all confirm relativity's predictions to extraordinary precision. The speed limit isn't theoretical speculation, it's experimentally verified countless times. Similarly, thermodynamic limits, like the impossibility of perpetual motion machines or perfect energy conversion, have never been violated despite centuries of attempts. These limits aren't arbitrary,
They emerge from fundamental principles like conservation of energy and the second law of thermodynamics. Given our uncertainty about whether power has limits, how should we proceed? Maintain humility. History is littered with confident proclamations that turned out wrong. Lord Kelvin thought physics was complete in 1900. Others declared heavier-than-air flight impossible shortly before the Wright brothers flew. Scientists insisted continents couldn't move until plate tectonics proved them wrong. We should maintain intellectual humility. Our current understanding is probably incomplete. Some of what we think are absolute limits might not be. But we should change our minds based on evidence, not speculation. Pursue knowledge carefully. We should continue researching fundamental physics, even exotic possibilities like faster-than-light travel or vacuum energy extraction. Scientific progress requires exploring ideas that seem impossible, but we should proceed carefully, especially with experiments that might have catastrophic consequences. Before creating microscopic black holes, tearing spacetime, or manipulating vacuum energy, we need extreme confidence in our theoretical understanding. The precautionary principle suggests, when an action might have unlimited downside, extraordinary caution is warranted. If we're unsure whether our experiments might trigger vacuum decay or other catastrophic effects, we shouldn't proceed until we're sure. Prepare for the possibility. Even if we don't believe unlimited power is accessible now, we should prepare for the possibility that future discoveries might unlock it. This means developing robust AI alignment. If we create super-intelligent AI before fully understanding its limitations, and if it gains access to unlimited power, misalignment could be catastrophic. Solving AI alignment while power remains limited gives us safety margins. Building resilient institutions. Societies need to be resilient enough to handle transformative discoveries without collapsing into conflict or chaos. Democratic institutions, international cooperation, and ethical frameworks should be strengthened now. Advancing philosophy and ethics. We need better philosophical frameworks for post-scarcity, post-mortal existence. We need ethics for beings with godlike power. These aren't just academic exercises. They might become practical necessities. Creating safeguards. Even if unlimited power seems impossible now, we should develop protocols for what to do if we discover it. How do we prevent misuse? How do we ensure fair access? How do we handle the societal disruptions? Embrace the mystery. Perhaps most importantly, we should embrace the fact that we don't fully understand reality. The universe is more strange and wonderful than our current theories capture. Whether power has limits or not, there are mysteries at the frontiers of physics that will reshape our understanding. That uncertainty is exciting, not frightening. It means discovery awaits. It means the future will bring insights we can't currently imagine. It means reality is richer than we know. What if power itself has no limit? Isn't just an academic question. It's perhaps the most important question we can ask about the future. If power is truly unlimited, or even if it's vastly greater than we currently access, then everything changes. The challenges that seem insurmountable today, climate change, resource scarcity, mortality, might become trivial. But new challenges would emerge, challenges we can barely conceive of now. If power is fundamentally limited, then we face a universe of constraints. We must learn to thrive within boundaries, to find meaning within scarcity, to accept that some dreams are impossible and some questions unanswerable. We don't yet know which universe we inhabit, but here's what we do know. For the past century, physics has repeatedly revealed that reality is stranger than we imagined. The universe has no obligation to match our intuitions or respect our comfortable assumptions. The speed of light seemed absolute, but space-time itself can expand faster than light. Time seemed uniform, but it dilates with speed and gravity. Particles seem to have definite positions, but they exist in superpositions of all possibilities. Energy seemed to require sources, but the vacuum teems with quantum fluctuations. Each of these discoveries revealed that limits we thought were absolute were more subtle, more contextual, or less fundamental than we assume. Perhaps the limits we still cling to will fall too. Perhaps the speed of light, Planck energy, and thermodynamic boundaries will turn out to be transitions rather than walls, thresholds where physics changes rather than ends. Or perhaps they'll stand. Perhaps we'll confirm that reality truly is bounded, that power has fundamental limits we cannot transcend, that some things are genuinely impossible. Either way, the question pushes us to the edge of human understanding. It forces us to examine our most basic assumptions about reality. It reminds us that the universe is under no obligation to be comprehensible or comfortable, and it challenges us to be worthy of whatever we discover. Because if power truly has no limit, then the only remaining question is, what will we do with unlimited power if we find it? That question, more than any physics equation, will determine humanity's ultimate fate. The universe may or may not have limits, but the story of whether we discover those limits, transcend them, or destroy ourselves trying is still being written. We're the authors, and the next chapter is about to begin. If this exploration into the nature of limits and the possibility of unlimited power changed how you think about reality, then you need to subscribe right now. We're living at a time when the boundaries between science fiction and science fact are blurring, and I'll be here to guide you through every breakthrough that challenges what we thought was possible. Drop a comment below. Do you think power has fundamental limits? Or are the boundaries we see just artifacts of incomplete understanding? Which limit would you most want to see broken? The speed of light, the maximum energy, or something else? Smash that like button if you want more deep dives into questions that exist at the intersection of physics, philosophy, and the future of everything. The universe's deepest mysteries are waiting. Let's discover them together.